My name's Ella Woods. I'm an early career researcher from the University of St Andrews in Scotland, and I would like to introduce our next presentation, which is on melting lake ice in northern Canada. And this is presented by Arash Rafat, who is a PhD student at Wilfrid, Laurier University in Canada. So welcome, Arash.
Thank you, Ella, for the kind words. My name is Arash Rafat. I am a PhD candidate from Wilfrid Laurier University out of Waterloo in Canada. And today I'll be discussing an often forgotten piece of the cryosphere, and that's ice covers over lakes. And in particular, their significance in northern Canada's transportation sector. So we'll start with the brief context behind where I'll be speaking about for Canada's north. It's about 150,000 inhabitants, broadly looking at communities north of 60 degrees in latitude. And there's about 53 of them that have been officially recognized. And when you look on a larger scale and overlay Canada's transportation network, you can see there's large inequalities where many of these communities are not in fact connected to all-season roads, such as highways, rail lines, or other road systems. And so many of these communities end up relying on what are known as winter roads or seasonally built roads. And so these roads cover land, frozen rivers, and lakes, and they're used to reduce the cost of transportation of vital goods and services to different communities, reduce the cost of medical supplies, as well as allow communities to practice their traditional practices on the lands where they were raised. And so current estimates place that around 10,000 kilometers of these roads are built each and every season across the country. And so what are winter roads? Broadly put, like I mentioned, there are seasonal roads built directly on land over lakes and rivers where you would clear the snow and use it for your either trucks or larger cargo to get to these different communities. So one example from a community we work in just south of the Arctic Circle, we have this picture here showing the ice road operations and during the actual building and design phase, where this community is not connected to an all-season road network and rely on this road for reducing the cost of things like fuel. In one particular region in Canada's north, known as the Northwest Territories, these roads are a complex mixture of not only all-season roads that are drivable year-round, but also these seasonally constructed roads. So of the about 1,450 kilometers of these roads, 37% of which are built each and every season. So it's quite a complex mixture of seasonal roads and all-season roads to make the broader transportation network. And on a larger scale, this is quite significant, in particular for Canada's greenhouse gas emissions from the transportation sector, which roughly account for about 25% of all emissions, depending on the year. And so looking forward into the future, any sort of sustainable designs in northern regions in subarctic or Arctic Canada will need to keep in mind CO2 emissions associated with any potential climate resilient design guidelines. And so winter roads are essential social and economic assets for northern Canada. And in particular with climate change, there are several key risks that have been identified. The first is risk to health and well-being of these communities. So with increased difficulties with accessing or building these roads, there's a decreased service and ability to actually ship this equipment. Not only that, there's an increased risk of casualties, in particular during the shipping operations. For one example here, where the tractor trailer has gone through the ice. The second of which is large for the security of Arctic Canada. Decreased transportation or ability to use frozen rivers and lakes constitutes a potential security threat as decreased mobility becomes top of mind to reach these rather isolated communities in a cost-effective means. The economy is always top of mind, in particular for the North, which relies on these roads. So with potential risks to climate change, we have things such as increased travel costs, which decreases the economic growth and potential of these communities who rely on actually building these roads, as many of these communities are employed during the actual building phase. And finally, the environment is key. Ice covers over lakes regulate the actual ecological systems and processes in many of these ecosystems and environments. And so any sort of changes to the thickness or timing of these ice covers has a dramatic influence on things such as the aquatic ecology, but also the terrestrial ecology for different threatened species. And so one thing I really wanted to highlight is the economic significance of these roads in the Northwest Territories. And one key example would be the Tibet to Contwaito Winter Road. And it's a road that's used to resupply remote diamond mines in the northeastern parts of the territory. And so the picture here is obtained from their website, which shows them hauling some of the equipment using an ice road over a frozen lake in this example, to resupply one of those mines in a cost-effective means. And why that's significant for this territory in particular is it accounts for about 18% of the GDP, looking at 2021 numbers. So it's quite a significant portion of their economic or their economy. Looking at it from a different perspective, we can look at, well, how much does it actually cost to resupply, in this case, these mines from shipping logistics or equipment. And you can see from one study, the costs are about 5 times roughly the price of alternative means of shipment, rather than building these roads every year and using them to resupply these remote mines. And so we place this in a broader context for all of Canada. The average annual air temperatures have risen about 1.7 to 2.3 degrees since 1948. However, the warming has been disproportionate across the country, as it's quite vast. And in particular, it's been extremely significant in northwestern portions of the country during the winter time, where already 4 to 6 degrees of warming have been experienced. So as you can imagine, there's a direct threat to not only these road networks, but many broader implications. And so we'll focus on winter roads here. There's been a study that's looked at, well, how much will it cost if we try to adapt to some of these future anticipated studies, looking again at this resupply road to these diamond mines. And in the worst case scenario, they looked at, it could be upwards of $350 million in additional funding required to look at things such as adapting scheduling, reduced timelines for how long the road is open, but also some of the design characteristics and potential for incorporating things such as portions of all-season road that may need to be built. And so there's 3 key things I wanted to highlight here. The first being the identified social and economic risks to these roads for operations. The second is decreasing seasonal lengths to which these roads are available for the public, but not only for the public, but also for resupplying different resource development projects. But from a scientific point of view, climate change has really been altering the actual physics of the process. So how the ice forms, how it freezes and continues to grow, and ultimately how it's melting. And really, that's the focus of my PhD research here, is looking at how the physics are changing over time and seeing if we can understand those changes, what might that look like into the future. And so that's the pillar of my own research, is looking at climate change impacts on the fundamental processes and using those fundamental processes to think, well, what does climate resiliency and adaptation look like for these northern transportation routes? And the real big question, what we're trying to get to is, well, then what, right? 50 years down the line, 100 years down the line, will these roads be able to be built? Do we need to consider what sustainable development might look like into the future, in a future where these roads may not be possible anymore? And so we do this through 2 broad approaches. The first is using observational data of snow and ice. And we do that using what we call smart sensors, and we'll touch on what that means shortly. But also what we've done is established a year-round station in a lake where we're able to take observations during the actual freezing of a lake and the melting process, where otherwise you won't be able to stand on the surface to collect measurements, right? If there's no ice, you can't exactly stand on open water. So that's a great benefit to us there. And we use this data and this information to improve some of the computer models that exist on snow and ice processes. And so ultimately, this presentation really focuses on the observational data, but I'll touch a little bit on the end of how that's incorporated into our ongoing work for modeling. And so since 2021, we've been monitoring ice and snow processes in 3 broad regions across the Northwest Territories. The first, looking to the top left there, is near the community of Delaney, where there's an ice road that crosses Great Bear Lake, which is Canada's largest lake. Looking at the second region near the capital city of Yellowknife, we have 4 different locations where we monitor processes for often traveled either ice roads or local snowmobile routes over frozen lakes. And then in the third region to the bottom right there is close to the community of Lutselk'e. And the region is completely isolated from any all-season road networks. And the monitoring there is to help inform local, for instance, ice travel for hunting practices or any sort of traditional practices the community may wish to use any information on for ice. And so I mentioned what those smart systems are like. They give us real-time information. And the sensor that we use is known as the Simba. So Simba is an acronym for Snow and Ice Mass Balance Apparatus. It's a bit of a mouthful, but Simba is nice and short. And it's essentially a long temperature chain that's 3 to 5 meters in length. And what it does is it gives you temperature measurements along the chain every 2 centimeters. So very high resolution along the length of the chain. And so we get those measurements every 15 minutes in time. And as you can imagine, with 2 centimeter intervals, you can form what are known as temperature profiles when you install these chains directly within the ice. And so you can see, based off of the different thermal properties of air, snow, ice, and water, how the actual ice is growing, how it's melting, and how the snowpack is changing over time. And so in one day, we can look at what that looks like using 1-hour observations of how temperature profiles are changing and ultimately how the ice is responding. So in this example, we're looking at hourly data over a period of roughly 24 hours where air temperatures went from about -43 to -3 degrees and how the ice is responding during that time. But on a seasonal approach, we can look at things such as observations over time, so over an entire season. And so using some of the data from this past ice season, looking at these different regions, we can begin to understand regional variabilities and how ice may be growing. We can also look at things such as when it may not be safe for local communities to get out onto the ice. And that really helps from not only an application point of view from our science, but to understand, again, some of that variability from the weather's point of view and how that's influencing the local ice conditions. And so one of the problems that we faced with the Simba sensors is we weren't able to install them when the ice was rather thin or when it's had melted away because you physically have to stand on the surface to put this instrument in. But to really understand the year-round cycle of ice, we needed data to be collected during the melting period and during the freezing period. So what we did is we put the Simba station or the Simba sensor on what we refer to as our floating research station. And what that allows us to do, paired with some measurements of weather conditions, is to get a holistic understanding and a year-round understanding of how the atmospheric interactions and open water conditions may be influencing things such as the melting period and the freezing period. And so since 2022, we've been able to do that. And the system is still operational, so it's giving us real-time data as we go. And so this is an ongoing monitoring effort. To give a better appreciation of what that looks like in different seasons, I've put the season between 2022 and 2023 here, just showing kind of the extent of the different weather conditions that we face. Typically in the summer times, it can go as high as maybe 25 to 28 degrees Celsius. in the winter down to the mid minus 40s. And looking at that ability to really capture that freezing and melting data is key. And so when we look at the freezing process, what that allows us to do in this plot is compare, well, how does the water freeze into ice and what do those different surfaces look like? Where here we're referring to the water surface in the red, the ice surface in the black, the snow surface in the blue, and the ice bottom in the pink. And so looking at interactions with the measured snowfall on the top axis, we can begin to understand, well, in a period of heightened snowfall, for instance, how does the ice respond? And so looking at ice core data and comparing it to these observations, it lets us understand, well, how thick is this whiter portion of the ice that is formed? And we refer to that as snow ice. And so you may be asking, well, why is snow ice so important in this context? Why do we care? And we care because commonly snow ice is a weaker form of ice. It's not able to support as much load as what would be known as congelation ice or ice that has congealed, the clear ice. And so looking back to that broader vision of design guidelines, understanding increasing trends in snowfall, in particular during the freezing period, is extremely key for adapting our future guidelines for understanding how we may account for some of these future variable conditions, in particular during the freezing period. And so on a larger scale, it allows us to understand things such as freezing processes in larger lakes. And so that's extremely key, again, from a community point of view, but also from scientific and practical interest. On the other side of things, so at the end of the season, we can begin to understand the melting period as well. So in the black line here, we're tracking the ice thicknesses over time, identifying, well, when does the ice first start to melt? When does the surface look like it's a little unstable, and ultimately when the ice is completely gone. And so when we have a trail camera on the shore of this lake, we can try to pair some of those observations together. So looking at the beginning of the melt period, somewhere around the middle of the period where we start seeing this typical mosaic type pattern forming, where we get patchy snow covers and partially melted ice. And these last two periods are key. And what happens is when the snow melts over, the ice begins to crumble into this pattern known as candles. And these candles are quite interesting because the ice remains quite thick at times, but the ability to hold any load whatsoever has completely disappeared. So as you can see here, the paddle just effortlessly goes through the ice. And so really from this measurements, what we want to do is be able to predict back from this point and see, well, what is the latest point that we can keep ice roads operating to a safe time frame, extending the period as long as possible, and of course, avoiding any sort of unsafe conditions. Typically, ice roads would close way before you would reach this point, but understanding the time it takes between the start of the melt season and when you get here, it can be key for future design guidance. And so what we did is we tested two rather common numerical models, so models of snow and ice that are applied for lakes and also for sea ice. And jointly with the Finnish Meteorological Institute, we conducted this modeling study based off some data for a Simba measuring ice conditions in a medium-sized lake in the Finnish Arctic. And what we identified based off of this study is the two key periods where models seem to fail are in fact the melting and the freezing periods. And so using some of that information that we've collected is quite vital to improving these models. And so using year-round observations over many years allows us to start to investigate some of these processes and why these models aren't able to capture these things. So looking at many years of data, we can start looking at, well, how does one year's weather compare to another year's weather, and how does that change the freezing process? So looking at 3 years of how the ice cover has formed and progressed, we can see quite a bit of variability. And again, each of these years had starkly different conditions. 1 year was quite dry, 1 year had record snowfall, and another year was a bit of a mix of two. So understanding these different conditions and how the ice cover is freezing and responding feeds into our numerical models and our conceptual-based understanding of these processes. Once again, we can look at the other side of things. So the melting season. We have 2 years of data so far, and what that 2 years of data has showed is that there is, again, quite a bit of a difference between the length of how this particular lake is melting. And so the 2025 data, of course, has not come in yet, but this is an ongoing effort. So we're going to continue monitoring to see how this variability may be changing with potentially variable weather in the springtime. And so how does this all fit together? The together point is an ongoing effort. So we're linking some of this melting data that we've collected over the last 2 years, the ice formation and the growth from all these different regions. And this year, we're really focused on understanding the strength of the ice covers. So we're using a hydraulic system where we're actually breaking the ice and seeing, well, at what point does the ice cover fail? And trying to incorporate that data with our existing monitoring of the formation, freezing, and growth is really key to improving some of these numerical models. And that's an ongoing effort that we're doing at the moment. Tying it all back together with how this fits into that broader pyramid vision, we're looking at future projections, right? So once we have this improved model, can we begin to investigate some of these things, such as in the case of extreme climate warming or different SSPs, what may the ice conditions look like into the future, and how can we plan for sustainable growth and development in subarctic and Arctic regions? And so applying this research is a large key for us, and it's really something that that we emphasize. So the first is providing things such as weekly maps to communities who rely on these ice conditions for traditional practices. So what we do as an example here is send out this weekly map, just showing the community in an easy graphic way what the ice conditions are like and how that may compare to last year's conditions. The second is looking at, in particular, Canada's National Adaptation Strategy, which has identified a reduced reliance on ice roads in the north. So we're well aware of these challenges. The question is, well, how are we going to implement these things into the future? And so that's really where the key should be focused, is applying some of these understandings and looking at ways, well, how are we actually going to finance this looking into the future? And so the presentation wouldn't be complete without speaking of some of the highlights that I've had over the years. It's been quite a privilege to work in some of these areas that are well-traveled and well-inhabited. And it's truly a pleasure to be able to work with these communities to not only visit, but also to work hand in hand with developing some of these policies is quite significant to me. And so finally, I would acknowledge that the work has been really a joint effort with our research group, the Remote Sensing and Environmental Change Research Lab, or RESEC for short, our funding partners, our community partners, as well as if you had any questions there, I put my email up. And feel free to reach out if you had any concerns or questions. And with that, I would love to leave it there and take any questions. Thank you. Are there any questions? You mind repeating the questions? Yes, so the local keys are the local partners are fundamental to any of the research that we're doing. And really, they are a pillar of any research for winter road guidelines. They are the experts, and we have been invited as guests. So really, as scientists who are working with these communities, we rely on these strong partnerships and working hand in hand with the local expertise. And the local expertise, in my opinion, has been invaluable. And as scientists, engineers, and researchers, really our key takeaway should be listening to what the community members have to say and really trying to apply and work hand in hand in tandem with the community. I can't speak to any of the negatives in particular from any one community. Broadly speaking, of course, any activities that involve construction have greenhouse gas emissions and some challenges associated with them. But that's something that's been identified, and it's a key challenge for many communities who may still be reliant on diesel fuel or fossil fuels to fund their local energy grid. So it's quite it's a work in progress, I would say, but many of these communities are well aware of the challenges and are putting in local efforts to drive towards a sustainable local development on local and regional scale. Yes, so it really depends on the region you're looking at. Some communities rely on these roads and have done that cost benefit analysis. And for many communities, it is still economically feasible to run these roads even for a few weeks at a time, because the cost of building an all-season road would be exorbitant. It wouldn't be economically feasible without any sort of partnership agreements. And so it remains quite a large challenge. The break point, I can't speak to any particular numbers because, of course, it would depend on future climate emissions and scenarios. But yes. I have heard of the concept. I am not familiar on any sort of the economic logistics of it, but I have heard that there is potential there. But of course, I haven't seen too much literature on it myself, so I can't speak. There's not much I suspect, but if it is a viable option, of course, communities are open to new ideas and working with partners. So if that does seem a viable alternative to the roads in the case that they're not economically feasible anymore, then I would reckon there would be interest by community. Yes. 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 Yeah. Yes. Yeah, so there has been some approaches that have looked at combinations of partially using winter roads connecting with certain overland segments that are all season. In particular, some of the most vulnerable regions for winter roads are the overland portions. In particular, the portages connecting different lakes and rivers. So there's been some discussions on, well, maybe building all season roads over certain sections to kind of mitigate against vulnerable regions. But again, it's very highly particular depending on the certain region you're looking at. Great. Thanks, everyone.